Okay, guys, do you have a deep desire to start? No? No one? Light desire, okay. So today I want to continue discussion of the groups. And today I want to explore the notion of a homomorphism and an isomorphism. Basically, well, we studied different groups, but now I want to have a tool to compare different groups. And the notion of a homomorphism helps us. So let me start with a definition. So, homomorphisms. Suppose we are given two groups. The group number 1 and group number 2. So this is the set of the group and this is the operation. And here is the set of the second group and the operation on the second group. Now, what is a homomorphism? So yeah, this is a definition. So a homomorphism is a map from one group to another. And it satisfies the following property. If you take two elements, G1 and G2 from the group G, and multiply them, the result must be the same as you take the image of each element, phi of G1 and phi of G2, and then multiply the images by the operation in the second group. So this is more or less, well, you can say that the map phi respects the operation. So it doesn't matter whether you apply the operation before the map or after the map. So in this case, phi is called a homomorphism. Okay, let me give you an example. Well, actually, several examples. Example number 1. The first group will be Z with addition, and the second group is Zn with addition modular n. Then we have a map which takes each element k to k modular n, which is basically the remainder of k modular n. So this map is a homomorphism because it doesn't matter whether you add k1 and k2 and then take the remainder, or you take the remainder of each number and then add them together modular n. So this is more or less the same. Okay, so this is the first example of a homomorphism. Another example, we have the group of permutations, and we have this group mu2, which is the set of plus minus 1, and the operation here is the usual multiplication, just multiplication of numbers. Then we have a map which takes each permutation to the sign. If the permutation is even, the sign of sigma is 1, and if the permutation is odd, the sign of sigma is minus 1. And we know that the sign of the product is equal to the product of the signs. So this is also a homomorphism. Another example, if we take the set of all invertible matrices over a field F, so just in case, this is the set of all matrices, square matrices, with determinant not being 0. So this is a group with respect to multiplication, and we have F star, which is the set of non-zero numbers from the field F. And the second set is also a group with respect to multiplication, the regular multiplication in the field. And then we have a map which takes each matrix A to its determinant. So this is the determinant map. And we also know that the determinant of the product of matrices is the product of determinants. So this is again a homomorphism. Here's another example. If we take R with addition and an R star with multiplication, where R star is the set of non-zero real numbers, and we have a map which takes each element to the exponent e to the power of x. Then this map takes the sum of elements to the product of elements. So basically, this rule also works. So this is another example of a homomorphism between one group and another group. Okay, so these are examples. Are there any questions regarding the examples or the definition? Okay. What should be next? Let's derive several basic properties of the homomorphism, like of any homomorphism. So here, the definition says that any homomorphism must respect the operations. But actually, the claim says that each homomorphism must take the neutral element of the group G to the neutral element of the group H, and the inverse element of any element of G to the inverse element inside H of the image. So let me formulate this. So if we have a homomorphism of groups, then if we take neutral element of G and apply phi, we will get the neutral element of H. So it also respects the neutral element. And the second one, if we take any element G small from G capital, then if we take G inverse and apply phi, the result will be the same if we apply phi to the element G and they take inverse in the group H. So this says that phi also respects the map of taking the inverse element. So let's prove this. By the way, is there anyone who can suggest the proof for the first one? Is there anyone who can see how to prove this? So this is everything that we know. We should derive the first item for this equality. Okay, let me show you how it works. So let's start with the definition of the element of the neutral element of the group G. Well, if we take the neutral element here and multiply it by itself, we will get the same element again. Now, we can apply our homomorphism to this equality. Then, because phi is a homomorphism, we will get this equality. But this equality in the group H. Okay? So this is an element of H, this is an element of H, and this is an element of H. So these all elements live here. And now, since this is a group, every element has an inverse. So for example, we can cancel one of the factors because we can multiply by phi 1G inverse, let's say, on the right. Then we can cancel these and these, and as the result, we will get this equality. So this is why we preserve the neutral element. So yeah, we should start with this equality and then just apply the homomorphism. Okay, who was able to follow? Are there any questions regarding this? Just in case. Okay. Now, the second part. Yep. Okay, you see here, well, what's written here is basically, if you denote this element by H, what's written here is H times H is equal to H, okay? Now, let's multiply it by the H inverse on the right. This is exactly what I did, okay? Then what you have on the left-hand side is H times H inverse equals H times H inverse. And this is an equality in the group H. By the definition of the inverse element, the product of H and H inverse is the neutral element of the group where these elements live. And these elements live in H, so this product must be the neutral element of H. Yep. Okay, no problem. The second part. Now we want to show that phi preserves G inverse. Again, let's take an arbitrary element G from G capital. Then, well, we have to use the definition of the inverse element. Well, what is the inverse element? This is an element with these two properties. Okay. Now, let's take the first one, and I want to apply the homomorphism phi to this equality. So because phi is a homomorphism, we will get this. But because of the first item, we'll already know that the image of the neutral element is the neutral element of the other group. So the right-hand side is actually one of H. So now we have this equality. This is equal to this. And now let's multiply by phi of J inverse on the left. When we multiply by this, we cancel this element, but when we multiply this by the element 1 on the right, we will get phi of G inverse itself. So the result will be phi of G inverse inside the parenthesis is equal to phi of G inverse outside. And this is how we prove the second part. Okay, who was able to follow, just in case? Okay, are there any questions regarding this? Should I repeat something? Okay, good. So what should be next? Okay, yeah. So my promise was to explain how to use homomorphism to compare two different groups. And the most important thing to do is to identify the same groups. For example, well, if you are given two sets, let's say a set with three elements A, B, and C, I said, and a set with three elements 1, 2, and 3. Well, technically, these are two different sets because they consist of different elements. Here we have letters and here we have numbers. But essentially, these two sets are exactly the same because they consist of the same amount of elements and just the names of the elements are different. So there is no point to distinguish these two sets. And if we don't want to distinguish two sets, we have to provide a bijection between two sets. So here we can say that A corresponds to 1, B corresponds to 2, and C corresponds to 3. This correspondence is a bijection. And what bijection technically means, it means that, well, these two sets are basically the same, but the elements of these sets have different names. And the bijection is somehow a translation. It translates a name from this vocabulary to the name from this vocabulary. So two sets are the same if there is a bijection between these two sets. But just the bijection, well, it knows nothing about the operation. So if we want to identify two groups, we want to say that the underlying sets are the same, but also the operation is also the same. So let me explain how to formulate this in terms of a homomorphism. So the definition. Suppose we're given two groups. Then a map from G to H is called an isomorphism. If the first property, phi must be a homomorphism, and the second one, phi is a bijection. So this is the definition of a homomorphism. So basically what it says, well, if you have a group G and a group H, the second part says that the map phi must be a bijection. So it means that you somehow identify the left-hand side with the right-hand side. So each element here corresponds to a unique element here. If it's G1 and G2, then these are H1 and H2. Well, they are phi of G1 and phi of G2. This is the second condition. So we have the same set for each group. But now, the first item says that phi respects the multiplication. So what does it mean? It means that you can take these two elements and multiply them, and you will get some new element, G1. And then you can take these two elements and multiply them using the operation of H, and you will get another element, H3. So the fact that phi is a homomorphism means that this product corresponds to this product under the same bijection. So phi takes this element to this one. So if phi takes this pair to this pair, then their product goes to the product of the other pair. So it somehow means that when you identify two sets, one operation becomes another one. So philosophically, what it means, well, it means that there is no difference which group to study. If you can identify one group with another one, you can change one group to another, and every property that you can prove for one group will be the same for the other one. So there is no difference between these two groups. So this is why we want to have the notion of an isomorphism, because it may happen that you have two groups which look completely different, but you still can provide an isomorphism between them, and it means that there is no difference between these two groups. Okay, probably I should give you an example. What kind of an example I have here? Okay, so let me show you several examples. No. A homomorphism, it resembles the notion of a linear map. So if you take the notion of a vector space, and just an arbitrary map which respects the structure of a vector space is a linear map. But when you want to say that two vector spaces are the same, you want to have a linear map which is a bijection at the same time. So this is a straightforward generalization from the case of vector spaces to the case of groups. Yeah, it may happen that you can have a lot of homomorphism between two groups. For example, a linear map is a homomorphism between vector spaces. And you know that you have a lot of different linear maps. They're described by different matrices. So here it's the same thing. You may have a lot of different homomorphisms. Okay, examples. Example number one. Let's take something interesting. Let's take R with addition and R strictly greater than 0 with multiplication. So this is the set of all real numbers, and this is the set of positive real numbers. Here the operation is addition, and here the operation is multiplication, okay? So the neutral element here is 0, the neutral element here is 1. Now, we have a map which takes each element x to the element e to the x. We already know that this is a homomorphism, but now it's a bijection, because we know that exponent takes each element to some positive element. And actually here we can provide an inverse map, which is just logarithm, natural logarithm. So if you have an element y, you can take it to the logarithm of y, and this map takes multiplication to addition. So these are two these maps are inverse to each other, so this map is definitely a bijection, and it respects the operations. Okay, this is one of the examples of an isomorphism. Another example. Let's take Z with addition. This is the first group. And the second group is the set of matrices of this form. And the operation is multiplication. Okay? So we have these 2 by 2 matrices. Here is 1 on the diagonal and some integer n in the upper right corner. Okay, now we have an obvious map from here to here, which takes each element n to the matrix of this form. And you may check that if you multiply this matrix with this matrix, you will get this one. And this is basically means that if you add 2 elements together here and apply this map, you will get this matrix. But if you take integers n and m and you first map them to matrices, you will get these 2, and then multiply them, the result will be the same. So this is the proof that the map is also a homomorphism. And this map is a bijection. It's just obvious. It's just by definition, because like literally the set of these matrices is 1-to-1 to the set of all integers. Well, this is not a very complicated example, but still, this is one of the examples that we may take. What should I give you next? Oh, yeah, and also, here is a third example. First of all, we have the set of complex numbers, let's say with addition. So they are given as pictures of this form, a plus bi, where a and b are real numbers. Then you can identify them with a set of matrices of the form where a and b are real numbers, and the operation is addition. Well, I mean, since the operation is just coordinate-wise, it's obvious that this map preserves the operation. But what you can do, you can exclude the 0 element here, the 0 matrix here, and replace addition by multiplication, and it still remains an isomorphism. So if you take, let me show you. So this map actually preserves 2 operations, addition and multiplication. So what you can do, you can take C star, which is the set of complex numbers without 0, with multiplication, and the set of matrices A minus B, BA, where A squared plus B squared is not equal to 0, and the operation here is also multiplication. Then, if you send this element to this matrix, this map is also a homomorphism, and it's a bijection just by definition. This is another example of an isomorphism. So it doesn't matter which model to use for the complex numbers. So these and these are exactly the same. So this is how to simulate complex numbers using 2 by 2 matrices. Okay, so these are examples of an isomorphism. So what should be next? The kernel, the image, and their properties. Okay, yeah. Well, just in case, probably you remember if you have a map, linear map between 2 vector spaces, well, it has 2 special subspaces. The first one lives in the source and called the kernel of the linear map. The other one lives in the target and it's called the image. So we have the same thing here for any homomorphism. So if we have a homomorphism between 2 groups, then the kernel of the homomorphism is the set of all elements from G capital such that phi of G is equal to 1 H. So we take all elements from G such that they go to the neutral element of H. Now, the image is just set theoretical image, which is the set of all elements phi. Let me rewrite it. The set of all elements phi of G in H, where G goes through all the elements of G capital. So this is basically phi of G capital. So the first one is called kernel. The second one is called image. So these are two subsets. This one lives here in G, the other one lives here in H. Well, what is important, these two subsets are actually subgroups. And the first subgroup is always normal. So let me prove this. The most embarrassing part of the lecture is trying to erase what was written 5 minutes ago, because it takes too much time. Okay, the claim. If we have a homomorphism between two groups, then the claim number 1, the kernel of phi is a normal subgroup of G. The second one, the image of phi is a subgroup of H. The third one, the phi is injective if and only if the kernel of phi consists of the neutral element of G only. And the fourth one, phi is surjective if and only if the image of phi is equal to the whole H. So these are basic properties of the kernel and the image. By the way, one of them is obvious. Which one? The second one. I have a better option. Which one? No. Okay, you had 4 attempts.
4.
Yep. So how lucky you are. Yeah, almost. From, it's like first attempt. Just say it, first attempt. We don't discuss other attempts. Yeah, this one is obvious. So what does it mean that phi is surjective? It means if you take all the elements from the left group, take their images, you will cover the whole group H, okay? But what is the image of phi? Is the set of all elements phi of G. So if image of phi is the same thing as H, it basically means that phi is surjective. So this is just by definition. So this one, we have nothing to prove here. It's obvious, okay? Who thinks that it was clear, just in case? Are there any questions regarding this part? Okay, good. Now, let's prove the first and the second one, and then we'll go to the third one. The first one, we need to prove that the kernel of phi is a normal subgroup. Now I have 1 million question. Who remember the definition of a subgroup? Okay, then there is the next question. Who thinks that I should recall the definition of a subgroup? Okay. Okay, we need to check that this one is a subgroup of G. So in order to check that the kernel of phi is a subgroup of G, we need to check three properties. The property number one, we need to prove that the neutral element of G is an element of kernel of phi. The second one, if two elements x and y are inside the kernel, then their product is also inside the kernel. And the third one, if an element x is in the kernel, then its inverse is in the kernel. So these are three properties that we have to check in order the kernel of phi to be a subgroup. Okay, now we want to prove that this is a normal subgroup. So the fourth property, which means that kernel is a normal subgroup, is this. For any element G from G capital and any element X from the kernel, we need to prove that Gx G inverse is also inside the kernel. That was one of the three equivalent properties how to check if a subgroup is normal or not. I just reformulated this property in terms of elements. It was formulated in terms of sets and their products. So, basically what I formulated was G kernel of phi times G inverse is a subset of the kernel of phi for every element G. So this is the same property as this one, but I just reformulated this in terms of elements. But this is exactly the same. So let's check this. Okay, well, how to check that something belongs to the kernel? Well, by the definition, kernel is defined by this equation. So if we want to check that an element G is inside the kernel, we must apply phi to the element G and check if the result is equal to the neutral element of H. So let's take the neutral element of G, and we should apply phi to the neutral element of G. But as we know, the result will be the neutral element of H. So just by the definition, the neutral element of G belongs to the kernel. That was the property number one. Now, the property number two. If we have two elements from the kernel, this means that phi of x is equal to 1h and phi of y is equal to 1h. Now we want to check if the product is also in the kernel. So we need to apply phi to the product and compute the result. Since phi is a homomorphism, it's a product of phi of x and phi of y. Each of them is equal to the neutral element of H, and the product will be just the neutral element of H. So this proves the property number two. And the similar thing shows the property number three. If we take an element from the kernel of phi, which means phi of x is equal to 1h, then we know that phi of x inverse is the same thing as phi of x, and then inverse. But since phi of x is 1h, then this is the same thing as this, and the result will be 1 of h, because the inverse to the neutral element is the neutral element itself. So this proves the first three properties. And it means that the kernel is definitely a subgroup. Who was able to follow? Are there any questions? Should I speed up? Okay, good. Just in case. Now, let's check that the kernel is a normal subgroup. So let's take an arbitrary element G from G capital. So we have no assumptions about this element. It's just a regular element of the group G. And an element X from the kernel, which means that phi of X is equal to 1h. And now we want to check that this element is also inside the kernel. So let's apply phi to this element. Okay, now I want to use the fact that phi is a homomorphism. Then this is the same thing as phi of G, phi of X, phi of G and inverse outside. Now, this element is the neutral element of H because X was from the kernel. So we can cancel this element, and the result will be phi of G times phi of G inverse. But the product of an element and the inverse element will be the neutral element. And since this is equality in the group H, this is the neutral element of H, just by definition of the inverse element. So yes, the image of this guy is the neutral element of H, so this property also holds. So the kernel is a normal subgroup. So this was the first part. Just in case, are there any questions? Good. Now, problem number 2. Okay, let's take the image. So, first of all, we need to check if the neutral element is in the image. Okay, how to prove that something belongs to the image? Well, in order to prove that something belongs to the image, we need to represent this element in this form. So we have to rewrite one of H in terms of the homomorphism phi. So we can write that the neutral element of H is equal to phi of the neutral element of G. This is what we know. So because of this equality, this element is rewritten in this form, but everything that is written in this form by definition is in the image. So this means that this guy is in the image of phi. So the first property, but for the image, holds. Now, if we take two elements, x and y, from the image of phi, we need to prove that their product is also in the image of phi. But again, x is equal to phi of G1 because it's from the image, just by definition, and y can be presented as phi of G2 because it's in the image. So the product, x times y, is the same thing as phi of G1 times phi of G2, and since phi is a homomorphism, we can rewrite it in this form. So as you can see, the product is also rewritten as phi of something. So it's in the image of phi. And the final one, if we take something from the image of phi, well, again, this is phi of G for some element G. We want to check if the element x inverse is also in the image of phi. But x inverse is the same thing as phi of G to the power of -1. And we know that we can move the -1 inside the parenthesis. And now it's rewritten in the form phi of something. But phi of something is always in the image. So this completes the proof of the second part. Who was able to follow? Good. Just in case, are there any questions? Also good. Now, the statement number 3. Statement number 3. So we want to prove that phi is injective if and only if the kernel is equal to 1. So let's prove left to right. Well, this is the simplest part. Who can see the proof? Just in case. Is there anyone who can see what should do? Okay. So what does it mean that phi is injective? Phi is injective, well, if the image of G1 and G2 is the same, then G1 and G2 is the same. So this is the definition of injectivity. So suppose phi is injective. we want to prove that the neutral element of G is the only element of the kernel. Since the kernel is a subgroup, the neutral element of G belongs to the kernel. Well, let's take any other element from the kernel. Let's denote it by G. Then, just by definition, phi of 1G is the neutral element of H, and phi of G is the neutral element of H. But now we have this equality that the image of this guy and the image of this guy is the same. But since phi is injective, it means that this guy coincides with this one. So by injectivity, the neutral element of G is equal to G small. So this proves that the only element of the kernel is just the neutral element of G, and there are no other elements. Okay, now the second part. I want to assume that the kernel of phi consists of one element only. Now I want to prove that phi is injective. So let's take two elements, G1 and G2 from G capital, and assume that phi of G1 is equal to phi of G2. And we want to derive from that G1 and G2 are the same. Okay, so we have this equality. This is equality in the group H. So let's multiply by phi of G2 inverse on the right. If we do this, we will get phi of G1, phi of G2 inverse is equal to the neutral element of H. Because we cancel the right-hand side and we multiply the left-hand side by this element on the right. So this is exactly what we get. But since phi is a homomorphism, we can move this power inside the parenthesis, and then we can multiply these two elements together. So the left-hand side can be rewritten in this form. Is it clear? Good. But now, you see, by definition, this element goes to the neutral element of H. So just by definition, this guy is in the kernel of phi. But by our assumption, the kernel of phi contains only one element, the neutral element of G, which means that there is only one option for this element. It must be the neutral element of G. But now, we take this equality and multiply by G2 on the right. Let's multiply this equality by G2 on the right. And we will get G1 is equal to G2. And this is exactly what we wanted to prove in this situation. And this completes the implication from right to left. And we're done. Just in case, are there any questions? I hope it should be clear. So what should be the next? Okay, now, you see, well, up to this moment, we don't have some instruments to produce new groups. Somehow we must invent a set, we must invent an operation, we must check that all the properties, all the axioms of the group are satisfied. Well, this is not an easy task. It's very convenient when you have some operation which allows you to produce new groups. For example, if you have two groups, you want to produce a new group using these two ones. And there are many different operations in algebra how to produce different groups. And I want to introduce the simplest one, which is called a direct product of groups. Okay, direct product. Well, suppose we have two groups, a group G and the group H. Now, well, I want to produce another group. Well, how to produce a group? Well, since group is a set, with an operation satisfying some axioms, first of all, I have to provide you with a set. Then I must define an operation on this set. And then I should check that all three axioms are satisfied. So let's start with a set. Well, as the set, I will take the Cartesian product or direct product of two sets. So this is just a set consisting of all possible pairs G and H, where G belongs to G capital and H belongs to H capital. So this is the set. Now, I should define the operation. So if we are given two elements, which means we're given two pairs, then I want to define the product of these two pairs. And there is the simplest way how to define the product is just to multiply the pairs element-wise. So let's just define this like this. So this is the operation. So now we have the data for the group. Well, since we have the data, we can check the axioms. First of all, well, this operation must be associative. Well, this is just a straightforward computation. If you multiply one pair, the other pair, and the third pair, it doesn't matter in which order you apply the operations. In the result, you will get just one triple here and another triple here. So, I hope that this thing is clear. Who's agree with me that the associativity is clear? Who thinks that we should check the associativity just in case? Okay, now, the second thing we need to check that we have a neutral element. What is the neutral element here? Yep, the pair of the neutral elements is the neutral element here. And the third one, for any element, we need to find its inverse. Well, this is the pair of inverses. So, indeed, these data satisfy all the properties that we need, and this will be a group. And this group is called a direct product of G and H. Oh, there are many different types of products. There is an amalgamated product, semi-direct product, and many other types. But this is the simplest possible way to produce a new group using G and H. Okay. What should... and yeah, by the way, here I gave you a definition in case of two groups. But it's clear that you can apply the same logic to define a product of several groups. So like it makes no difference to define a product of finitely many groups. So I don't want to do some stupid work, so I hope it's clear how to do this. What should be next? Nice. And we have enough. Okay. So now I want to switch to a very specific class of groups. One of the reasons why I want to do this is because, well, this class of groups is, we will be used it a lot in cryptography and in other applications. So let's start with finite abelian groups. Well, the name is self-explanatory. G is a finite abelian group if G is a commutative group with finitely many elements. So it must be commutative. This is what abelian means, and it's finite. So it has finitely many elements. Now, we know several examples of finite abelian groups. Zn plus, it's a finite abelian group. Currently, this was the only example that we had. But since we have this operation, we can produce a product of two finite abelian groups, or even three finite abelian groups. Okay? So this is also a finite abelian group. And by the way, if this group has n elements, this one has m elements, and this one has k elements, then how many elements are in the product? Yep, exactly. M times n times k. So this is also a finite abelian group. Well, it happens that there are no other groups, in the sense that if you have a finite abelian group, it's always isomorphic to a direct product of finitely many cyclic groups like this. So let me state the claim. So if G is a finite abelian group, then G is isomorphic. Well, I didn't introduce this notation, but if a group is isomorphic to another group, we have this notation, like an arrow and a tilde above it. Then the group G is isomorphic to a direct product of cyclic groups. I'm not going to prove this claim, because, well, the proof is not complicated, but it's long and tedious. You just need some computations with matrices with integer coefficients, but you also need to know something about quotient groups, and still I don't want to define quotient groups in general, so I want to skip the definition of this proof. And actually the proof, it doesn't provide you with any information or any technique. Like, it's like a proof on its own, without, like, it proves the result, but there are no other benefits of knowing the proof. Like, it doesn't help you to solve problems or something like that. So, but basically, when we're given a finite abelian group, we may think about a group like this. Now, here's an example. Let me give an example here. If you take, let's say, Z8 star with multiplication. Okay. Well, it's clear that this is an abelian group, and it has finitely many elements. So it must be isomorphic to a group like this. And actually, there is an isomorphism to Z2 times Z2. And by the way, what I didn't say, the operation here is addition modular n1 and k in each coordinate, okay? So the operation here is multiplication, and the operation here is addition modular 2 in each factor. And, well, the question now is, how do you construct this isomorphism? Well, there are many ways to produce this isomorphism, but one of them is the following. So let's list all the elements here. So this is the set of all odd numbers from 0 to 8. 1, 3, 5, and 7. And you may check that if you take 1 to element 0, 0. So 1 is the neutral element here. The pair 0, 0 is the neutral element here. So 1 must go to the pair 0, 0. Then you can take the element 3 to the pair 1, 0, and the element 5 to the pair 0, 1. Then the element 7 must go to the pair 1, 1. So if we define a map like this, well, a straightforward computation shows you that this map respects the operations, both operations. So this is an isomorphism. This is not the only one isomorphism. You can actually take the element 3 to this one, the element 7 to this one, then the element 5 goes to this one. Like, there are many different isomorphisms. It's not like some specific isomorphism, just a random isomorphism between these two groups. But what is important, it doesn't matter how this group looks like. If it's finite abelian group, it must be isomorphic to a group like this. And what is the benefit of this fact? Well, it's not clear how to deal with this guy. because like the structure of this group is unclear, like how to deal with the elements here, like how to find an order of an element, how to multiply the elements, etc. But if you're given this group, it's clear how to deal with the elements of this group, because like you have just pairs of zeros and ones and just apply the operation, the addition modular 2. Like the right-hand side is easier to deal with than the left-hand side. So that's how you use this isomorphism. The hard part is actually for a given finite abelian group to find such an isomorphism. This is the hard part. But if you are given such an isomorphism, then you can efficiently solve different problems using this isomorphism. Okay. What should be next? This is what I... Okay. Who is familiar with the Chinese remainder theorem? Okay. Now, well, I'll try to show you how this result is related to the case of finite abelian groups. Let me give you one remark before we start with the Chinese remainder theorem. You see here what I told you. I told you that this group is isomorphic to a group like this. So basically, it means that there exists a sequence of n1 and k such that this isomorphism exists. But I didn't mention how unique these numbers are. Well, it's clear that you can permute the factors and it doesn't affect the group. It's still be the same group. But what happens, well, actually, these numbers are not unique. They need not be unique. It may happen that the same group is isomorphic to a product of cyclic groups, but with different factors. And we want to know what are different options, like how to distinguish when this representation defines the same group. Well, in order to do that, we need a tool. And the main tool here is the Chinese remainder theorem. Chinese remainder theorem. Okay, suppose we're given two numbers and an m, and they are coprime. Two positive integer numbers. Then we have a group of remainders modular n times m. Okay, and we can produce the product zn times zm. So this is a group where the operation is addition modular n times m, and this is a group which is a direct product of two groups. Here the operation is addition modular n, and here the operation is addition modular m. Now we have a map from the left-hand side to the right-hand side, which takes a remainder k, and it goes to k modular n, k modular m. So let's denote this map by phi capital. Now, the claim says that first, phi capital is a homomorphism. And the part number two, phi is a bijection. So this is the Chinese remainder theorem. Okay. Does it resemble anything you know about the Chinese remainder theorem? Probably the Chinese remainder theorem you knew was like that. If you're given two remainders, one modular n, another one modular m, then you can find a remainder modular n times m, such that its remainder modular n is the first remainder and its remainder modular m is the second one. So the Chinese remainder theorem you already know is just the claim that this map is surjective. Is it clear now? who was able to follow the last statement? Okay, the Chinese remainder theorem, you're probably familiar with, says that this map is surjective because it's usually formulated like this. If you are given two remainders, A and B, modular n and m respectively, then you can find another remainder, k, modular n times m, such that the remainder of k modular n is A and the remainder of k modular m is B. So this is basically the surjectivity of this map. And yeah, well, when you don't familiar with the notion of a group, this is the best thing you can prove here because this is the most difficult part of the proof. But in general, what you can say that here you have an isomorphism between two structures. The left group and the right group are the same, like the isomorphic groups. In particular, this says like Z6 is isomorphic to Z2 times Z3 because 2 and 3 are coprime. But Z4 is not isomorphic Z2 times Z2. Well, first of all, the result does not apply here because 2 and 2 are not coprime. But why these two are not isomorphic? Well, because here you have an element of order 4, which is 1. And here the order of each element is either 1 or 2. So like there is no element of order 4 in the right-hand side. So these groups cannot be isomorphic because under isomorphism, the order of an element is preserved. So that's why these two groups are not isomorphic. So basically, this instrument allows us to rewrite a cyclic group in terms of a product of other cyclic groups. And you can apply it into the both directions. And what happens, well, this is the only thing that makes this representation non-unique. So if you have two representations of two finite abelian groups, you can always go from one representation to another one, applying the Chinese remainder theorem for the factors. Okay? So that's why it's an important tool, because it describes how to check if these two guys define the same group. Well, I'll go back to this thing after the proof, but before we're going to prove this, are there any questions regarding the statement itself? Should I clarify something regarding the statement? Are there any questions? Okay, good. Okay, first of all, let's prove that phi is a homomorphism. Well, in order to prove that phi is a homomorphism, we need to check that it respects the operations. So let's take two remainders k1 and k2 and inside z and m. Okay? Now, we want to check that phi of k1 plus k2 modular nm. So this is what I did here. I just applied the operation to k1 and k2 and then applied the map phi. We want to check that the result will be the same as and here the dot is the dot denotes the operation on the right-hand side. Well, this is just a component-wise addition. So let me denote it by star, actually. It will be easier to distinguish it with the product. So this is what we want to check. We don't know if it's true or not, okay? So now let's compute by definition the left-hand side. So we have k1 plus k2 modular n times m, and then we should map this element to this pair. So we want to take k1 plus k2 modular n m, and then we take it modular n. And the second element will be k1 plus k2 modular n m, and then we take it modular m. But you know, if you take a remainder with respect to n times m, and then a remainder with respect to n, this is the same as to take the remainder with respect to the smaller one. Like there will be no difference. So this is the same as k1 plus k2 modular n, k1 plus k2 modular m. So this is the left-hand side. Yep.
How do we call this legend? I and circle.
This one?
Yeah.
This is phi capital. Okay, was it clear, just in case? Okay, good. Now, let's compute the right-hand side. So this thing is k1 modular n, k2 modular n. And now we want to apply the operation with k2 modular n, k1, oh, I'm sorry, k1, k1, k2, k2 modular m. Here it is. So this one goes to here, and this one goes to here, and then we want to apply the operation. Now, how do we apply the operation? We just take the first coordinates and apply the operation from the first group. So here we need to apply addition modular n. So k1 modular n plus k2 modular n, and then the result modular n is the same thing as k1 plus k2 modular n. And again, if we take k1 modular m plus k2 modular m, and then the result modular m, we will get exactly the same. So this is the right-hand side, and they are the same. Who was able to follow? Are there any questions regarding the proof? Okay, so now we know that this is a homomorphism. We want to prove that this homomorphism is a bijection. But you see, if we have a set, it's very difficult to prove that a map from one set to another one is a bijection. So we need to prove that it's injective and surjective at the same time. But here, we know that injectivity and surjectivity depends on the kernel and the image. So, first of all, I want to check that phi is injective. So let's prove that phi is injective. So this is just a short notation for the term injective. Okay, in order to do this, we need to prove that the kernel of phi consists of the zero element only. So let's compute the kernel of phi. So what is the kernel of phi by definition? Well, it consists of elements k from z and m such that k is equal to 0 modular n and k is equal to 0 modular m. Well, because so what is the zero element here, the neutral element here? The neutral element here is the pair 0, 0. So when k goes to 0, 0, it means that k modular n is 0 and k modular m is 0. But what does it mean? It means that k is divisible by n and k is divisible by m. So in other words, k is divisible by n and k is divisible by m. So now we use the fact that n and m are coprime. If they are coprime, then the product divides k. So since n and m are coprime, then their product divides k. But k was a remainder. It was a number between 0 and n times m minus 1. So it's divisible by n times m if and only if it's 0. There is only one option. So from this, it happens that k is equal to 0. So we started with an arbitrary element from the kernel, and we proved that this arbitrary element must be 0. So there are no other elements in the kernel. So the kernel of phi capital is equal, well, it consists of the 0 element only. That's it. Who was able to follow? Good. Now we know that this map is injective. How to prove that this map is surjective? Well, there is an easy way, because this set is finite and this set is finite, and we have an injective map between these two sets. So if we can prove that these two sets have exactly the same amount of elements, then this map is automatically surjective. But how many elements do we have here? N times m, by definition. Here we have n elements, here we have elements, and we have n times m pairs. So we have exactly the same amount of elements. So Zm and m has the same amount of elements as the other group. So and since phi is injective, phi is surjective. So this is the short term for being surjective. Okay, so this is the Chinese remainder theorem. Just in case, are there any questions regarding the statement or the proof? Cool. Now I want to keep this here. That's why I want to rewrite something here. May I clear the central part? Okay. Oh, yep. Because I want to keep the initial claim there, and I want to compare the claim with the two claims I want to formulate right now. So I'd rather write on the central whiteboard. So what should be here? An example. Okay. Yep. So, okay. The claim. So this will be a classification of finite abelian groups. So what does it mean, a classification? Well, classification means that, well, you can give a list of finite abelian groups such that every pair of these groups are different in the sense they are not isomorphic. So they're different groups. And then for any other abelian groups, it will be isomorphic to one of them. So somehow it will be like a complete list of all possible finite abelian groups. So this is the classification. The problem here, why this is not a classification, because some of these groups will be isomorphic. But the list of all these groups is complete in the sense that if you are given any finite abelian group, it's isomorphic to one of these. So now I just want to somehow refine this representation in a way that we will get like a unique representation in this kind of form for any finite abelian group. And there are two different ways to classify finite abelian groups. The way number one, let me say G is a finite abelian group. I want to say it here, is a finite abelian group. Now, the claim number one says that there is a sequence of integers d1, d2, etc., dk, where d1 is strictly greater than 1, it divides d2, it divides d3, and so on, such that G is isomorphic to this type of products. And this representation is unique. Well, this is in case, well, when I'm saying d1 is strictly greater than 1, what I mean is, well, this happens if and only if G is not trivial. Because in case when G is trivial, it may happen that you have to take the element 1 here, but if the group G consists of more than one element, then you can find this sequence of dividing of number that each one is dividing the other one, such that G is presented in this form. Well, for example, let me give you an example of this form. Let's take Z2 times Z6 times Z30. So here, 2 divides 6, 6 divides 30. This is an example of this kind of representation. So if you are given two groups in this kind of representation, then they're isomorphic if and only if this sequence of numbers is the same. So if I give you something like, let's say, Z2 times Z2 times Z90, it has the same amount of elements. So like if two groups have different amount of elements, they are not isomorphic because the underlying sets are not the same. But in this case, you see, here we have sequence of 2, 6, and 30, and here 2, 2, and 90. Well, and the two sequences are not the same, because here is the difference and here is the difference. So these two groups are not isomorphic. So this representation is unique in this sense. So it allows you to classify all possible groups, all possible finite abelian groups. well, this is the part of the claim. So this uniqueness means that if you are given two groups in this form, like you see, they are explicit in this form. And if this sequence of numbers is not equal to this sequence of numbers, like the same sequence, then the group automatically are not isomorphic. This is the part of the, so this is what this uniqueness means, okay? So that's how, because like it's unclear what uniqueness actually means. So it means exactly this. So it's a very powerful statement. Like you just look at the picture defining the group, and like if you see this difference, they're different. That's it. Nothing to prove. Okay. And by the way, and here you see like the left-hand side is written in this form. You just have one element d1. Okay. The left-hand side, and the right-hand side is not presented in this form. You see, 2 does not divide 3. And since the right-hand side doesn't satisfy this property, you don't have this uniqueness. But if the both hands, the left and the right-hand side are presented in the same way, there will be exactly the same pictures for these two groups. Okay, so this is the classification number 1, and the classification number 2 says that, well, you can present the group G in the following form. Z P1 to the K1, Z P R to the KR, where Pi R prime, Ki are strictly greater than 0. And, well, if you order these elements like P1 is strictly smaller than P2, is strictly smaller than P3, and so on. And, well, that's, no, it's not like this. Oh, well, here, P1 is a prime number, like 2, okay? And this is the power, like 2 to the power of 3. So it's just a power of a prime number. So you can represent the group G as the product of cyclic groups, but the order of each cycle group is just a power of prime. So you can always rewrite it like this. Well, because, well, if you can rewrite every group G like this, then using the Chinese remainder theorem, you can split each cyclic group into the product of prime factors. For example, if you have something like, well, in case of 6, it's just 2 and 3, but in case of 12, it will be 4 and 3. And 4 is a power of 2. It's not a prime number, but it's a power of a prime number. So you can always split your group in this form. And now, what about uniqueness? Well, the uniqueness here is up to permutation of factors. So if you have two representations of this form, they're the same if and only if you can permute some factors and you will get the other representation. So it is unique up to permutation. So let me clarify what it means, just in case. So for example, I can write something like this: Z2 times Z2 square times Z3 times Z3 square. So I can rewrite it in the form like Z3 square times Z2 times Z3 times Z2 square. Well, I just apply the permutation of factors. It's clear that this is the same group. So this is the only option how these two representations may be distinct, may be different. But in this case, well, I mean, somehow it's clear how to organize the computation. You may like move all the factors with 2 here, then all the factors with 3, then all the factors with 5, and then you just compare the powers. So somehow, like, this is not an issue when you have to permute them, because it's easy to identify different representations. And yeah, and so this is how unique this one. So these are two possible options to describe all possible finite abelian groups. Okay, and this is how you clarify like this statement. Like you make it a bit stronger. Okay, that's more or less everything that I wanted to explain during this lecture. Like, are there any questions or something?
Story?
It will be, like in a minute.
I see.
Тогда всем спасибо, ребят.
Спасибо.